Have you ever really stopped to think about the journey water takes before it gets to your glass? It's not magic. It's actually a complex, highly engineered process, and it's all designed to protect public health. So today, we're going to follow a single drop of water on its incredible transformation, all the way from a raw reservoir to your tap. Our journey kicks off right here, at the Vavunathivu tank in Sri Lanka. This is the source, a massive reservoir that's mostly fed by monsoon rainwater. It's a vital resource, no doubt, but this raw water is a long way from being drinkable. It's carrying sediment, organic matter, and, potentially harmful microorganisms. And that really is the million-dollar question for any water engineer, isn't it? How do we take this natural, but pretty challenging, source water and systematically turn it into something that's not just clean, but verifiably safe for thousands and thousands of people every single day? Well, it's a fascinating mix of physics, chemistry, and biology. To answer that, we're going to follow the exact path the water takes. We'll start with the plant's mission, trace the water from the reservoir, dive into the chemistry that makes it clear, see how all the solids get removed, understand the final safety checks, and then, finally, see how it all measures up to the national standard.
Okay, so first things first. Let's get to know the facility that's at the heart of this whole operation, the Vavunathivu Water Treatment Plant.
This plant is run by the National Water Supply and Drainage Board, and it is a critical piece of infrastructure for the entire Batticaloa district. I mean, it has the capacity to treat around 40,000 cubic meters of water every single day. Its entire reason for being is public health. Now here's what's really interesting. The plant isn't just trying to make the water look clean. It's working toward a legally mandated target, the Sri Lankan standard SLS 614. This table here shows just a few of the key parameters. Every single process we're about to see is designed to hit these exact numbers. And we're going to pay special attention to that turbidity target of 2 NTU, because the tiny particles that make water cloudy can actually act like shields for harmful bacteria, protecting them from disinfectants. All right, let's move to the very beginning of the physical process and see how the water actually gets from that reservoir into the treatment facility itself. To really appreciate the engineering here, you first have to understand the challenge. The water in the Vavunathivu tank is super variable. During the monsoon season, rains wash in a ton of sediment, making the water highly turbid. That's the scientific term for cloudy. Then, during the warmer, drier periods, the risk of microbial contamination shoots up. So the plant's design has to be tough enough to handle these wild seasonal swings. The very first point of contact is the WTP inlet. You can think of it like the front door to the plant. Its job is to manage the flow of water coming in and to do the very first bit of cleaning by screening out all the big stuff, leaves, branches, you name it, anything that just doesn't belong. So this slide gives us a great roadmap of the whole treatment train. After the inlet, the water moves through this series of carefully orchestrated steps. We've got chemical treatment, physical separation, some pretty advanced filtration, and finally, disinfection. Only then is it ready for storage and distribution. Now we get to the really clever part, using chemistry to deal with all that cloudiness. This is where the magic of making water clear really begins to happen. The main tool for the job here is a chemical called polyaluminum chloride, or PaCl for short. See, most of the tiny particles that cause turbidity have a negative surface charge, which causes them to repel each other and just stay suspended in the water. PaCl is a coagulant with a strong positive charge, so when you add it, it neutralizes those particles, allowing these other weak forces to take over so they can start clumping together. So once the particles are neutralized, the very next step is flocculation. This is all about encouraging those tiny particles to meet up and form bigger groups. The water is mixed very gently, which promotes collisions that build these larger, heavier clumps we call flocks. And right here, you can actually see the flocculation channels in action. The water flows through these basins, and that gentle hydraulic mixing creates the perfect conditions for those flocks to grow. The whole goal is to make them big and dense enough so they can be easily removed in the next stage. So we formed the flocks. Now, how in the world do we get them out of the water? Let's move on to the separation stages. The Vavunathivu plant uses what's called a multi-barrier approach for separation. First up is dissolved air flotation, or DAF. It's a really elegant process, actually. Water is saturated with air under pressure. Then, when that pressure is released, millions of microscopic bubbles form, attach themselves to the flocks, and float them right up to the surface where they can be skimmed off. It's especially good for low-density particles like algae.
After DAF, the water passes through sand filters, which physically strain out any remaining suspended particles. And the final polishing step is filtration through granular activated carbon, or GAC. This stuff is a highly porous material that removes dissolved organic compounds, the things that cause taste and odor issues, through a process called adsorption.
Okay, so the water is now looking crystal clear, but now we have to deal with the threats we can't see. This is the critical disinfection step, and it's all about making sure the water is biologically safe.
Chemical dosing actually happens at multiple points. Lime is added to adjust the pH, making sure the water isn't corrosive to the pipes and that the disinfection process that comes next is effective. Chlorine is the primary disinfectant. You might have a pre-chlorine dose to help control algae early on, while the post-chlorine dose is the main kill step for any bacteria and viruses that are left.
The key here isn't just adding chlorine, it's adding the right amount of chlorine. The goal is to have a residual chlorine level of up to 1.0 part per million in the final water. This small, totally safe amount of chlorine stays in the water as it travels through the pipes, and it provides a protective barrier against any potential recontamination on its way to your home.
So after all of these steps, the chemical reactions, the physical separations, the disinfection, what do we actually have? Let's take a look at the result.
This side-by-side comparison just perfectly captures the transformation. On the left, you've got the raw, cloudy, turbid water from the Unichai tank, and on the right, the final product, clear, safe, and ready to go. This is the daily achievement of water treatment engineering. It's pretty amazing.
And ultimately, that's what this is all about. Every pump, every filter, every single chemical dose is part of this huge integrated system with one single non-negotiable purpose: to safeguard the health of the community it serves. It's a fundamental pillar of modern society.
And that brings us to a final thought. This process works incredibly well, but it was designed based on historical climate patterns. So for the next generation of engineers, maybe some of you watching, the question becomes, how do you adapt a system like this to handle the future? A future with more intense monsoon rains causing extreme turbidity and longer droughts that concentrate contaminants? That is the challenge that lies ahead.